Hello dear students, welcome to the lecture series on Verilog HDL. This is module number 3, lecture number 18. Now these are the topics that were covered in the previous lecture. In the last lecture, we try to look upon what are the different gate primitives that are available in the Verilog, that is AND, NAND, buff not, and we try to figure out with an examples how the system with these gate primitives work. Now we try to look upon some specific examples related to buff not and NAND gate primitives, and we try to get the simulations out of these two primitives. Now today in this lecture we will be mainly focusing on different array instances and certain Verilog programs with respect to array instances and different gate primitives. Now what are basically array instances? Now there are many situations when repetitive instances are required. Like for example, I'll be dealing with one particular circuit and I'll be requiring many NAND gates or many AND gates. Now these instances differ from each other only by the index of the vector to which they are connected. In the sense, all the pattern of those gates remain same, the working remains same, but the number of instances I'll be requiring would be more. Now to simplify specification of such instances, Verilog HDL allows an array of primitive instances to be defined. How we are going to define and how we are going to use that we will see in the form of simulation. So let me quickly go to the simulation window. I'll have opened up this particular Xilinx setup over here. Now here is my Verilog primitive program. Yeah, now I'll try to show you two different set of programs, one without using the array primitives, the other one with array primitives, and we'll try to figure out the differences, what will happen if I use array primitives and what will happen if I don't use array primitives, what are the sort of advantages using array primitives. Now as you can see on your screen, I'll just zoom it. As you can see on your screen, this is a program of a simple NAND gate wherein there are multiple NAND gates are defined. So I have 8 NAND gates over here. So all the NAND gates are used with the help of a predefined primitive NAND. As you can see, it is shown in the blue colored wordings. So this is my instance, n underscore gate 1, n underscore gate 2, like that I have n underscore gate 8. Now in order to define 8 NAND gates, I should be requiring different set of terminals for all the 8 gates. And since the functionality is same, then definitely I can be instantiating through one primitive NAND. As you can see, everywhere I have instantiated from NAND. So because I am dealing with an AND gate, but the number of the nature of not nature the name of the parameters that you can see over here are different. Here you say out1, in1, out2, in2, out3, in3. So there are different set of parameters that are defined for all the gates, and when I define all these parameters here, then I need to be defining it over here. So in my module section in the beginning of my program, I need to be defining them, out1, out2, out3, so and out8, and I need to define them as output. Similarly, I need to be defining all the inputs and I need to declare it as input from in1 to in8. Then I'll be writing the program. Now if I just run this program, let me try to run this program. So I have already written the program over here, gate primitives. Now you should be aware that if there are many programs written under a single project, this indicates this is the current module. As you can see over here, see, this particular patch indicates this is the current module or the present top module, which means even if you run this program, the output what you are going to get will be with respect to mux, because this is set as a current module. So in order to get the output related to this particular array primitives program, I need to set this array primitive program as the top module. As you can see over here, right click, set as top module, it will ask, then you say yes. Now see here, so now your present program is the top level module. So now let me synthesize over here. Yes, so all the without any errors and warnings, it has been synthesized. Then I'll go to simulation. Now, like I was telling, it is always a good practice to run any Verilog program through the test benches. So what I'll do, I have created the test bench. How do you create the test bench? In your implementation section, you just right click on this and just say new source, and here we need to be selecting Verilog test fixture, and you name the test bench name and then keep on saying next, and that will be automatically added to the present file, which is your array primitives. Like that, I have created the test bench. Now always remember, when you are in this implementation form and when you create the test bench, it won't be visible. To make your test bench visible, you have to jump down to the simulation window over here. Now as you can see over here, array primitives, below that there is something called as UUT, that is unit under test. So this is my test bench which I have created. So this is my program which I wrote just now, and the test bench is always sitting on top of your program. So here also, as you can see in the left side corner of your simulation window, this is your program, and on top of that your array primitive test bench program will be sitting. You double click on that and the test bench will open. Now normally all the parameters will be made available to the test benches. The only thing that you should be worried, or you should be giving the input is, so here I have given the inputs 1010 1010, and then the second input 1110 So I have given the inputs, and then let's try to get the results with respect to these inputs. So what I did over here, I have written the program of the simple AND gate, wherein I am instantiating 8 NAND gates but without array primitives, and I have written the test bench over here, and then the test bench looks like this. Now if I run, so remember, when you run this program, that is array primitives, then only this output related to this program will come. At that time, you as an user has to specify the inputs. But if you run the test bench, since already you have given the inputs will be chosen directly in the simulation window. So let us try to simulate this array primitives program, which are written without the help of array primitives. So I'll just do the simulation behavioral button. So that will open up your simulation window. Now I won't be testing all the outputs, rather I'll be giving the inputs to one or two values. So we can be giving force clock or constant. I'll be giving the inputs to in1 and in2, and the moment I give the inputs to in1 and in2, the output is visible in the terminal out1. So let me simulate that. So as you can see, the output is visible at both out1 and out2 terminal. That's because I in1 is for out1 and in2 is for out2. So both the gates with respect to out1 and out2, that is n underscore gate 1 and underscore gate 2, will be simulated, and you can see the respective waveforms. Now this is without gate primitives. Now let's try to simulate with gate primitives. Now with gate primitives, I'll try to comment out this entire structure. So I'll try to open up this program and comment out of this. Now this is the program wherein I have written the Verilog program using gate primitives, array primitives. So wherein in the main module, you are just specifying whatever the main outputs and inputs, and depending on the number of gates that you want to simulate, you will be mentioning all those terms in the form of arrays. Like for example, let's say this entire circuit has got 7 output terminals, and there is no need to mention out1, out2, out3 till out7. I can mention the output in the form of array. So let's say in the subsequent stages, I want to increase the number of output terminals from 7 to 10. What I can do, rather than mentioning out 1 till out 10 here in the main module, I can just change this MSB value in the array from 7 to 10. So that will ensure that there are 10 output terminals from 1 to 10. Similarly, there are 10 input 1 variables from input 1 to input 10. Similarly, there are 10 input variable 2. So by doing this, I can be ensuring the complexity of the program is reduced drastically. Now this program I'll be simulating with the help of test bench, because I need to give the inputs in the form of array. So for that I have already created the test bench. So by creating new source, selecting the Verilog test picture, naming it and clicking on next, and that has resulted into this program. So this is what is the test bench for the program using array primitives. So I have mentioned the inputs and input 1 and input 2 in the form of an array. Now these are your input, which means input 1, input 2, input 3, input 4, input 5, input 6, 7, 8. So these are different inputs. So if I want to now simulate, before that let me try to synthesize it. I'll be synthesizing it. Once the synthesis is done, yes, it is perfect, then I'll be going for simulation. So simulation, I'll be simulating the test bench. So this is my test bench, so I'll be simulating it. Now no need to give the inputs from the user, that is no need to manual inputs. I can give, yes. Now why this z term is coming over here? Now that's because there is something mismatch in the variables. See, in the main program you wrote from 1 to 7, in the test bench you have written it as from 0 to 7. So let me change that in the main program only. So this will be 0 to 7, and then in the main program also it is 0 to 7. So I'll save it. I'll again resynthesize it. For any small changes you do in the main program, you are supposed to do the synthesis. Okay, there's an error which says, yeah, n gate is 8 bits, but must be either 1 or 7 bit. So that is here in the test bench 0 to 7. That means from 0 to 7 it results into 8, but whereas here in the program you are mentioning it out as 1 to 7. So let me change it. So I'll again do the synthesis. Now it should work fine. Let's wait. Yes, go to simulation. I'll do the simulation. Now I should be getting all the inputs in the form of the expected result. So let's try to simulate this once again. Now I should be getting all the results. Yes, there it is. So inputs is an array. Input 1 is an array of 8 bit. Input 2 is an array of 8 bit with different values, and based on those different values I'll be getting my output. So this is how I can check the result. Now the main advantage of using the array primitives is it will reduce the complexity of the program drastically. So that was presented in this particular simulation. Now moving ahead, now we have something called as gate level multiplexer. Now let's take an example of a multiplexer written in the gate level modeling and try to simulate that again. So I have there it is. So this is my gate level program. Now this is an example of a multiplexer. Now let's try to simulate this and try to get the results with respect to different primitives. See, as you can see, the predefined primitives are being used over here. The not is being used, and is being used, or is being used, and always, like I was mentioning in my previous lecture, the first term will be always the output. Like you can see, why not, why, all the why terms are your output, and the out term is the output. So this is the main program of your 4:1 mux, and to understand this mux program I need to be knowing the circuit diagram, because I have written the program in the gate level modeling, so definitely circuit diagram becomes very important. So let's try to get the circuit diagram of this 4:1 mux. There it is. So this is the circuit diagram of 4:1 mux that I was talking, with a truth table and a block diagram. Now for this circuit, using the gate level primitives, which means using the standard gates that are available in the Verilog, I'll be writing the Verilog code for this particular multiplexer. So let's try to figure out which are the inputs and which are the outputs and which are my intermediate connections, which we call it as wire. I0, I1, I2, I3 as well as S0, S1, which are my select lines, will be acting as input. Y0, Y1, Y2, Y3 will be acting as the outputs for individual AND gates, whereas out is acting as an output for the entire multiplexer. So which means I can name Y0, Y1, Y2, Y3 as wires, because these are not my main output. Since I am discussing with respect to multiplexer, what I will be worried is with respect to this out terminal, that is my final output, and all the intermediate outputs will be termed as wire. Similarly, you can see S1N, S0N are your intermediate outputs of the NOT gate. So I can even say these are acting as a wire. So on this note, let's try to write the program. As you can see over here, I have defined all the inputs and outputs in my main module, and I declare them, and then I mention them which are the intermediate connections or the internal declarations as wires, and then I'll try to instantiate different gates using predefined gates or predefined primitives. So not is one gate. Now you can just see over here, instantiation of these predefined gates are not done with respect to individual gates, because I haven't mentioned any instances over here. Now again it will lead to confusion, because now looking at these two NOT gates S1N, S1, so now since the circuit is very simple, it is easy to understand. Like just go to S1N, I'll just find where is S1N. S1N is here, so which means this particular line of code is relevant to this NOT gate. But what if I just mention the instance N1, so that even ensures that this NOT gate is behaving, or this NOT gate is renamed as N1. So it is with respect to that, I'll mention this as N2. So which is respect to this is output, and S0 is my input. First term is output, and here I have AND gate primitives A1, A2, A3, and A4. Now the main reason why that instances were missed, because whenever you use predefined gates, there is no strict and mandatory rule that you should write the instances. That's the reason instances were missed out. Even if you don't write the instances, the program will work properly, but it is always a best practice to mention the instances, because as the circuit becomes more and more complex, your instances will play an crucial role in understanding the behavior of the circuit. Let me quickly take with respect to this and A3. So Y2 is the output, remaining 3 are your inputs. So Y2 is the output, remaining 3. Which are the remaining 3 terminals? I2, S1, and then S0N. I2, S1, S0N. And finally, I have the OR gate with an instance O1, and then for this OR gate, out is my output, Y0, Y1, Y2, Y3 will be acting as my input. So let's try to simulate this mux, but before simulating I need to ensure this would be made as a top module. So then we'll go with the synthesis option. Once the synthesis is properly done with no errors and warnings like it is shown over here, then I'll move to simulation. Now I have my mux written over here. Now for this mux, the basic agenda of taking this example, because you are aware that this is how the mux program looks, but what I am trying to focus here is how exactly the test bench of this multiplexer looks. So I have created a test bench. Again, creating the test bench is very simple. You have to just click on the main program where you can find and say new source and say Verilog test picture, give the name of the test bench and keep saying next. By doing that, a test bench just above this program will be created, which looks something like this. All these things whichever I am highlighting over here will be predefined things till here. In fact, till here all these things will be predefined. Now what extra thing that I have added over here is the display function, which we have learned in my module 2. So why this is being added? Just in order to display the contents of individual terminals in the simulation window along with the waveforms. It is just to figure out exact values at a different instance of time. Now here you can see what is the different instance of time I have written here. #1, which means after every 1 second the display action is called and relevant values will be displayed. And as you can see, dollar display signal can be initiated something like this in the double inverted quote, whatever the terms you want to display, and the in number system in which you want to display. Since all these are binary format, so I'll be using percentage %b, and then what are the actual name that you are used in the program, that I need to mention over here. So everywhere it will be I0, I1, I2, I3. So I would like to display all the input variables. I would also like to display S0 and S1 based on different values of S0, S1, what will be the output. Similarly, based on S0 and S1 value, like for 0, 1, what will be my output. Rather than just displaying the output, I would also like to display for what value of select lines the output has resulted. So like that, I have displayed 5 uh, set of instructions. Now let's try to simulate this. So once I try to run this, now this is my waveform window. Since already the inputs were given in the simulation, like here, what were the initial inputs you have given? See, 1, 0, 1, 0. That is I0, I1, I2, I3. So in the simulation waveforms, so you will be seeing the results with respect to these values, as you can see. Yes. See, I0 is 1, I1 is 0, I2 is 1, I3 is 0. So with respect to these values, the output has resulted along with S0 and S1. So for different value of inputs, whatever you have mentioned, I can see the output. Now why this dollar display? What is the extra benefit of using this dollar display? As you can just come down below the simulation window, you can just see here the display action taking place. Like I was discussing over here, I have displayed 5 different display values. So that has been displayed. The first display was to display all the inputs, and what were the inputs you have given in the simulation window? These were the inputs, and that has been displayed. In the second display, what is that I had displayed over here? That is S1 value, S0 value, and then out. So for S1 of 0, for S0 of 0, what will be the output? See, for S1 of 0, S0 of 0, output will be 1. From where this output 1 came? Now again, let me go back to the circuit. Let's say S0, S1 are 0, 0. 0, 0 means Y0 should be selected. So this 0 goes over here. Any NAND gate with a 1 input as 0 will result into 0. So output of this AND gate Y2 will be 0. Since S0 is also 0, this comes over here for I1, even the output of this will be 0. S1 is 0, that will be termed as 1, it goes over here, which means still I have the hopes of turning on this Y0. S0 is 0, this is 1, so Y2 is 1. But since S0 S1 was having a 0 value, this is off anyhow, and now S0 is 0 means even this is off. So only one option that is left out, or the only one AND gate which could be on is Y0, and that on of that AND gate depends on the value of the inputs that you are giving. So what are the other two inputs? One is I0, whatever the value of I0 comes. So by the way, what was your S1? 0. 0 converts to 1. 1 goes over here. So it could be on. 0 is here. 0 converts to 1. It goes over here. So 1, 1. So depending on the I0 value, if I0 is 0, the answer will be 0. If I0 is 1, answer will be 1. Now in our case, what is the I0 value? I0 value is 1. So let's try to see. Since I0 value was 1, output will be 1. So that's how I can display depending on the select lines. Similar action happens with respect to other select lines. You can just keep on giving the values S1 0, S0 1. Based on these select lines, 3 of the AND gates will be turned off, and only one transistor will be turned on, and that output of that particular AND gate depends on the type of input that is going to be given in the form of I0, I1, I2, I3. So that's what I explained with respect to the first case. Similarly, for S1 S naught with 1 0, what will be the output? S1 S naught with 1 1, what will be the output? 1 1 in the sense 1 1 is third output, as you can see over here, 1 1, that will make y3 as on, so which means I3 will be coming at the output, so which means I3 will be seen at the y3. So what is the value of I3? I3 was 0, hence output was also will also be 0. So this is how I can make use of display $display function in order to check the output in the test bench by displaying them. So this is with respect to your multiplexer program. Now on the similar line, we have one more example which we have already seen from the day one of the lecture, that is 4-bit triple carry full adder. Now the basic idea of choosing this example is to see that how the gate primitives can be used in order to build this carry full adder, and before building that I need to be building the 1-bit full adder, and in order to build the 1-bit full adder, it's a simple full adder circuit. I'll be using the XOR and XOR multiple XOR and AND gates in order to build. Now as you can see, this is my one full adder. I'll be defining the inputs and outputs, and I'll be defining my intermediate wires. S1, C1, S2 are my wires, and then I'll be instantiating stating the XOR gates. Again, like I was telling, when you use predefined gates, no need to mention the instances, but again it is a best practice to name that instance. Here, although I have not mentioned the instance, but it is always the best practice to name the instance, like x1, x2, a1, a2, something like that. So I have this XOR, like whenever I use predefined logic gate primitives, the first term will be output. So S1 is the output, that's what it is coming over here. Remaining two are my inputs, A and B are my inputs with respect to this XOR gate. Now with respect to this AND gate, C1 is the output and then A, B are my inputs. See, please remember, with respect to this gate, C1 is acting as an output. But what is with respect to this entire circuit, what is the nature of C1? With respect to this entire circuit, the nature of C1 is it is behaving as a wire because it's an intermediate connection. But when I write a program, I'll be breaking down the components with respect to individual gates, and then I'll be writing the program. Similarly, I have XOR. This XOR, the one term is the output term is sum, and the input one is S1 and the other input is C underscore I in. So like that I have defined different values for all the gates, and then once I have my 1-bit full adder with me, I'll be building the 4-bit ripple carry full adder whose circuit looks something like this. So I have used 4 different full adder circuits, that is 1-bit full adder circuit, and I'll be calling 4 times 1-bit full adder. How does that look? It is looking something like this. Again, see, when I define all these modules, inputs and outputs, these are defined with respect to the circuit what you are seeing, or the circuit for which you are writing the Verilog code. Like for example, which are the inputs and outputs over here? Overall sum is my output, C out is my output, A, B and C in are my input. But if I look into this entire structure, how many inputs are there? Like there are A0, A1, A0, A1, A2, A3, B0, B1, B2, B3, and then C in. So altogether 4 plus 4, 8 plus 1, 9. 9 inputs are there. But in my definition, what I am writing, I have defined something like this. That's because in my next stage, I'll be defining or I'll be declaring all these inputs in the form of arrays. So there comes the advantage of array primitives. So what does this mean? Input 3 colon 0 a comma b, which means a is a 4-bit width value having its range from a0 till a3, and we have a0 till a3. Similarly, I have b. B goes from b0 till b3, making it a 4-bit. Then I have an individual input c in, c underscore in, which is a single bit entity, hence I have not mixed up this thing. Then I have all the wires. So these are my intermediate wires. Which are my intermediate wires? C1, C2, C3, all these things are my intermediate wires. And what will be my outputs? Sum of 0, sum of 1, sum of 2, sum of 3, because I have defined in the form of arrays. Again, if I don't want to wish to use the array primitives, then I won't be using the bracket. Rather, I can write S0, sum 0, sum 1, sum 2, sum 3, and I need to be mentioning here 4 times output sum 0, sum 1, comma sum 2, comma sum 3. And again, even here also, I need to be mentioning sum 0, comma sum 1, comma sum 2, comma sum 3. All 4 parameters I need to be mentioning if I am not using them in the form of array. So that is the biggest advantage when you use the array primitives. So I'll be calling 4, since this is the circuit for which I am writing an Verilog code, and this happens to be 4-bit triple carry full adder, and there are 4 full adders. So I'll be calling 4 times the full adder which I have written over here. The name of that circuit, the name of that 1-bit full adder is full add. So I'll be calling it 4 times. Full add FA naught. FA naught is the instance name. FA naught again. Full add is not the primitive defined in the Verilog library. It is a user defined primitive, hence I'll be writing the instance, but nevertheless writing an instance is always the best practice. Now let's say full add FA0. In this circuit, where is my FA0? Here is my FA0, and for this FA0, which are my outputs and inputs, sum of 0 is my output, and that's the reason I'm writing it as first. Rest all things are input. C1 is input, A of 0, B of 0, C underscore in. A1 is in A of 0, B of 0, C in is one input, and sum of 0 and C1, both two of them are output, hence those two are specified in the beginning. Now once this is written, full add FA0, the program or this instance try to find where is full add. It tries in its database, it reaches there and try to compare or match these terminals with full add terminals where you are written. So the program comes over here, FA0, it searches full add, it goes to full add, here is my full add. Now these components and these components, sorry, will be matched, which means sum of 0. What is the nature of sum of 0? For me, I can say sum of 0 is the output because I can see it, but for the compiler, what is the nature? Sum of 0 behaves like sum of your individual full adder circuit. And what is the nature of sum? Sum is the output. So which means the first term whatever you have written behaves as the output. So this is my output. What will be C1 behavior? C1 behaves, it goes to full add. Full add program is here. C1 matches to C out. Now mapping happens with respect to this circuit and that circuit. In that circuit it is C1 in the main circuit. In the sub circuit it is C out. So what is C out here? C out is nothing but the carry output of this 1-bit full adder. And what is the nature of carry output? The nature of carry output is it is behaving as output, which means second term whatever you write in the main program, the main program is here. This is my second program. So C1 behaves like a C out of an individual 1-bit full adder. So the nature of C1 is output. What is A of 0? A of 0, I can say that it is input, but what is the nature? It is a third terminal. It goes over here. A of 0 behaves the same way how your A was behaving in your single 1-bit adder. And what is the nature of A? A is your input. Like that, B, C are also compared with the remaining terminals, and similarly all the full adders FA0, FA1, FA2, FA3 will be compared with the individual full adder 1-bit full adder circuit, and then those 4 full adders will be instantiated, and that will result into this circuit in the back end, and that will simulate this entire full adder by when I give the different inputs with respect to A and B. So this is how your array primitives will come into picture, and they will save lot of things with respect to time, with respect to complexity, and with respect to execution of the program. Now let me go ahead one step ahead. So that's what you have learned with respect to the array gate array primitives. Let's try to come down to what are the typical examination questions that could be asked in the examination. Simple 3 programs that could be possibly asked in exam. Explain gate array, explain array of instances with an example, wherein you can take in any instances example, like simple NAND gate examples we took in today's lecture, that can be taken out. And then a program can be asked like write Verilog description of a full 1-bit full adder using Verilog primitives, rather than just asking 1-bit full adder. See the difference using, when they say using Verilog primitives, it means you are supposed to use predefined gates. Again, when they mention multiplexers using Verilog primitives, you are supposed to use the predefined gates. So that's how the questions can be twisted out. Now, what are the applications of this today's lecture? The entire module or the lecture focused on understanding the fundamentals of Verilog primitives, and the application includes writing simple programs that comprehend various digital circuits using the simple gate primitives. So that's where you find the application of today's lecture. Now, to summarize, so in this lecture we have learned how to initiate array of instance and to write Verilog description of certain logic circuits using basic Verilog gate primitives that are predefined in nature. And since all these concepts require recalling and understanding of certain facts, this entire lecture comes under level 2 of Bloom's taxonomy, mapping to course outcome number 2. So this is what is dealt in this today's lecture. Hope to see you in the next lecture. Thank you for the patience listening. Thank you once again.